So thanks a lot for this invitation back in online. So I hope I still manage to deal with my iPad. Okay, so I will speak about groups of birational transformations, and like the motivation of everything. This comes like from the Cremona groups. So let me say what this is. So I'm interested in the group of birational transformations of a projective space. So the birational maps going from Pn to Pn. And I'm particularly interested also when I'm working not necessarily over an algebraically closed field, but over any field. So birational maps defined over a field K. So this is the Cremona group of rank n over the field K. Okay, so there is a long history about this group, and there are many questions that one can ask. But so for today, I want to think of two questions. So, okay, and also, of course, instead of looking at the group of birational transformation of the projective space, one can also just ask about the structure of any beer X. So let's say X is a smooth projective variety. Okay, so the first question is some beer X generated by elements of finite order? Okay, and let me maybe also say a word. So these group of birational transformations, I'm particularly interested when they are large, okay? And this is like classically the case when we are working over the projective space. Otherwise, sometimes they are just finite, okay? But so this is why I'm interested in projective space. And a second question is like, do we have large quotients of Brx? So what I mean by that, so I'm asking for group homomorphisms going from Brx to some group G. And basically here I ask that G is large. So whatever that means. I mean, that's not a precise question. And I mean, somehow these questions are related, and maybe like, let me also say that when we ask G to be abelian, then this gives the question about the abelianization of Brx. Okay. So in a way, when you ask about finding all the group homomorphisms to an abelian group, this is like the same as to ask about the abelianization of that group. And also another thing I want to mention is that when we take the kernel of such a group homomorphism, then of course this gives us a normal subgroup. And so the existence of such normal subgroups, this is not a trivial thing, not at all. So also existence of such homomorphism it was a big question. Okay, so what do we know about these two questions? So for the Cremona group, we know the following things. So Cremona group over a field K. So let's first look at when n is 2. So now the classical case is when n is 2 and when the field is algebraically closed. And in this case, we have a theorem, or sorry, yeah, okay. So we have a theorem by Noether and Castelnuovo. And so this is a theorem from like 120 years ago. So this is like the classical setting. And it says that in this case, the Cremona group is generated by PGL3 of K and only one additional element. I write it sigma, and sigma is in affine coordinates the map that is sends xy onto 1 over x, 1 over y. So this is the standard quadratic transformation. Now, why does it answer the first question in this case? That's simple. So this is an involution, this sigma. Okay, and in fact, also PGL3 is generated by involutions. You can check this also just by taking the elementary matrices, and you can decompose them into involutions. So this is generated by involutions. So the whole group is generated by involutions. So yeah, it is generated by elements of finite order. And in fact, the same statement is true for when K is any perfect field. So and this is done by Stefan Lamy and myself. Okay, and we also, so this is the answer for question 1. So the answer is yes. Maybe I should write this. And we also have constructions of quotients. And so and what we have for so all the constructions that we have, we get a G which is a free product of direct sums of Z mod 2 Z. Okay, and so constructions are done by Zimmermann, Lamy Zimmermann, and by myself. And these work for when K is perfect and K is not algebraically closed. Okay, and also maybe as a remark, since we have that it's generated by involutions, like the abelianization is of the form some direct sum of Z mod 2 sets. So somehow, yeah, this is what we can get in dimension 2. Now for what happens in higher dimensions. So when n is, let's say, when n is 3, then the answer to the first question, so about Brix being generated by elements of finite order, is no. And this is in a recent preprint by Schinder and Lin. And in fact, one can rephrase what they are doing by saying that they construct a group homomorphism to G equals Z. Okay, so because we have a group homomorphism to Z, the group of birational transformation cannot be generated by elements of finite order. And so this works for n equals 3 and k, when k is sorry, the rational numbers. But they also have a construction. It also works for when n is at least 4, and so this works also for k equals c. Okay, and then so the answer is again no, with the g equals z. Okay. But before that, there were other constructions for g. So other constructions. And what all other constructions are again of the form when G is a free product of direct sum of Z mod 2. And the first such construction was by Blanc, Lamy, and Zimmermann. And in fact, their proof was the first one to show that there exists non-trivial normal subgroups of the Cremona group of rank at least 3. Okay. So the construction of this group homomorphism was the one to show that the Cremona group is not a simple group. But there are also other constructions. There is also a construction due to Tsikas and one by Blanc, Yasinsky. Okay, so what will I speak about today? So like one question is that like all of these things, they were for when X is a projective space. So what happens now if X is not a projective space, but maybe something which is close to a projective space? So let me phrase it like this. What if X is only geometrically rational? Okay, so this means birational to a projective space over the algebraic closure, but not over the field itself. So this brings me to the first theorem. So I will call this theorem A. So BSY stands for Blanc, myself, and Egor Yasinsky. So let S be a non-trivial Severi-Brauer surface. So what does this mean? This means that S over the algebraic closure is isomorphic to P2, but S over our field, K, is not isomorphic to P2 over our field. So this is maybe strange if you're not used to these kind of things. But so even if you don't care about such surfaces, actually with the theorem B, you will see that it actually can be interesting also when you're not, when you're only interested over the complex numbers, say. Okay, but so let me first write down what the theorem A is. So then set PD to be the points on S of degree D, and we mod out by automorphisms of S. So I just take the points of degree D up to the automorphisms. Then there exists a surjective group homomorphism from BRS to a direct sum of Z mod 3 free product with a free product of Z. And the indexing sets are here is we get P6, so points of degree 6. And here we get P3, but we need to take 1 point out. So let me just any point, P0. So for any P0 in P3. So now what is interesting here is that we, first of all, we have here a Z, and here we have a Z mod 3. So when you compare this with what we've seen before, I mean, here before we always have something with Z mod 2 or with Z. Okay. But also I want to mention here that for the surface case, so here, all the quotients are with Z mod 2, so we didn't have any Z or any Z mod 3. So this Z mod 3, this is also something interesting that comes up here. Now, so also what this means in particular, if P6 is not empty, then BRS is not generated by elements of finite order. Okay. And so actually this is, as far as I know, this is the first example of a geometrically rational surface that is not generated by elements of finite order. Okay, a few remarks I want to make to this statement. So for 2 points, PQ on S of degree 3, we have that they are so how should I write this? So I know, okay, like equivalent with respect to the automorphism of S. If and only if P and Q have the same splitting field. Which is the case if and only if P and Q have the same, have K isomorphic residue fields. So for points of degree 3, we know how what this action of odd S means for points of degree 3. And so this is not necessarily obvious, so this is a lemma. And another remark I want to know is like, okay, is this group homomorphism even non-trivial? I mean, if it's just trivial, then of course you can construct. Oh no, yeah, okay, then it's, I mean, okay, anyways. So what I want to say is that P3 consists of at least 2 elements. So in fact, this means that this group homomorphism is not trivial. So group homo is not trivial. And also there do exist examples where this P6 is not empty, and so we really get examples. Okay, so also we are not the first to study the group of birational transformations of Severi-Brauer surfaces. So Schramov, he studied especially finite subgroups. Studied finite subgroups of BRS. And in particular, he saw that all finite subgroups are of odd order. So in particular, there exist no involutions in this group of birational transformations. So let me say no involutions. Okay, so this was theorem A. Now theorem B is now in a different setting. Now, for all n, at least 4, there exists a group homomorphism from the Cremona group of rank 4 to free product of Z, where the indexing set has the cardinality of C. So I would call this a large quotient. So because in particular what this means that because so this is the free group over the set of the complex numbers. Okay, so what this means is so in particular for any group G with cardinality of G at most the one of C, then there exists a group homomorphism to G. Okay, so any group that has the cardinality at most C is a quotient of the Cremona group. So now when you look at theorem A and theorem B, they look maybe rather different, and maybe it's not so obvious how we go from one to the other. So how we do that is the following idea. So from theorem A to theorem B. So the idea is we take, well, we want X to be a fibration such that the general fiber is a non-trivial Severi-Brauer surface over the field C of B. Okay, so now this here is my perfect field that I will work over. Okay, and now we have the following fact. If B is a curve, then C of B is something which is called a C1 field. And what this means, or what this implies, is that there are no non-trivial Severi-Brauer surfaces over that field. Then CB, how should I write this? So is C1, whatever that means. And so there exist no non-trivial Severi-Brauer surfaces over C of B. Okay. So this means that if we want to do this idea, then we need that the dimension of our base B has at least dimension 2. Okay. If we want that something like this exists. So need that the dimension of B is at least 2. But then this implies that the dimension of X is at least 4, right? Because the general fiber is a surface. So let me so the dimension of X is the dimension of B plus 2. Okay, so which is at least 4. And now this explains why we have our statement of theorem B for n at least 4. This is why we require n at least 4. So our strategy does not work for n equals 3. Okay. And so actually such fibrations, we're not the first to study them. These are also studied by Maeda and by Kresch and Schinkel. And so actually what we also need, so our idea is that we take such a fibration. I mean, we search for such a fibration, and we want that X is rational, right? So in this way, we can study B or X, and this is then conjugate to the Cremona group when X is rational, okay? So what we also need is that X is rational. And now actually the rationality of such a variety is a subtle question, because Kresch and Schinkel, they showed that there are examples that are not even stably rational. Examples of such varieties that are not even stably rational. Okay. So we also need to make sure that we get something that is rational. Okay. Okay, so the strategy for both theorems is with the Sarkisov program. And so okay, so let me write it down. So strategy. So basically, okay, we want to construct group homomorphisms. Now, the way we do that is, so what we need generators to define our group homomorphism on the generators. And then we need to check with the relations whether this is actually well defined, what we are constructing. Need generators and relations. Now, we are not directly taking generators of our group, so of the Cremona group, but we are considering a groupoid. So we call this Mori of X. And so this consists of the birational maps from some x1 to x2. So birational, where x1, x2 are Mori fiber spaces that are birational to X. So I will, if you don't know what a Mori fiber space is, I will define it later. So, okay, so this is not a group, right? Because we just take any Mori fiber spaces that are birational to X, and so we just, you can't necessarily compose these birational maps in this groupoid. And now what the Sarkisov program states. So this is by Gorty, Iskovsky, Haken-McKernan. And it can be stated to say that Mori of X is generated by some simple birational maps, which are called Sarkisov links. And also this, I will give a definition afterwards. But maybe let me say for surfaces, these Sarkisov links, think of them as you have x1 to x2. And we take a birational map such that the minimal resolution such that these two maps are the blow up of at most one closed point. So this is what I mean by a simple or an easy birational map. Okay, we just blow up one point and then we contract one more point at most. Okay. We will see this later again. So okay, so let me give the definition for that, and I will now okay, so let me say what I want to speak about in the next minutes, or like until, well, in my talk. So we have these two theorems. We have theorem A and theorem B. One is for surfaces over perfect fields, and the other one is in higher dimensions. So I will focus now on theorem A. So I will focus on the surface case, because this is like an important part of the whole thing to see like what's going on. Theorem B, the proof of theorem B is much more involved, and I would have no chance of saying anything too meaningful in a short time. Okay, so this is why I will focus on the surface case. And I mean, in higher dimension, everything just gets also much more technical. So to give you an idea, I will stick with surfaces for now. So from now, surfaces. And let's say K a perfect field. Maybe I should have said perfect field. For example, you take Q a finite field, or you take C of, let's say, T1, T2. And actually, C T1, T2, this is like what is important then for the generalization to higher dimensions. Okay, so the Sarkisov program. Let me give definition. So this is the definition for surfaces, okay? So X surface, then P from X to B is a rank R vibration. If pi is surjective with connected fibers, and so the dimension of B is strictly smaller than the dimension of X, which is 2. X and B are smooth, and the relative pica rank of X over B is equal to R. And what we also need is that the anti-canonical divisor of X is pi ample. So pi ample, that just means that minus kx times c is positive for all curves C that are contracted by pi. Okay, so this is the definition of a rank R vibration. Now, why do I give you this definition? So a remark. So if R equals to 1, then a rank R vibration corresponds exactly to the Mori fiber spaces. So let me write it out. Mori fiber space. Now, if you know what a Mori fiber space is, you will see that that this is exactly the definition of a Mori fiber space. And if you don't know what a Mori fiber space is, then you can take this as a definition. And now, what is very nice with this definition is also so when we take R equals 2, these are exactly the Sarkis of links. So now again, if you know what a Sarkis link is, you can check that this is exactly the same. And if you don't know what a Sarkis link is, you can take this as a definition. So let me say how before. Okay, so before I had I said that this is what you should. Wow, what happened? That this is what you should think of Sarkis of links. So let me combine these two points of view. So we have x1 to x2, a birational map. And I mean, x1 over b1 is a Mori fiber space, and x2 over b2 is a Mori fiber space. And now a Sarkis link in the definition of rank 2 vibration. This is now the y on top over a base b. Okay. So this thing here going from y to b, this is rank 2. Okay. And now if you start with the definition of a rank 2 vibration, because the relative pica rank is 2 in that case, then you have exactly 2 extremal contractions. So you can contract exactly to, there are exactly 2 ways to contract. And so this is how you get these 2. Okay, so we have, so when R is 1, we have Mori fiber spaces. R is 2, we have Sarkis of links. So you can ask what happens with R is 3. And this is still interesting because these encode exactly the relations between circuits of links. So I will not say more about this now, but later I will show you a picture of that. Okay, so we want to study the birational transformations of a Severi-Brauer surface. And I say that the generators of our groupoid are the circuits of links. So let's see what kind of circuits of links do we have. Okay, and for this I need to give you some facts about Severi-Brauer surfaces. So let S a non-trivial Severi-Brauer surface. Now, if P is a closed point on S, then actually 3 divides the degree of that point. Okay. So this means that there is no rational point, there is no point of degree 2, there is no point of degree 4, 5, okay. And like the classical way to deal with Severi-Brauer varieties is via central simple algebras. So there is a one-to-one correspondence between Severi-Brauer varieties and central simple algebras. And now you can think that when you have an algebra, you can define an opposite algebra by just saying you make a new multiplication. So you say you define now A times B to be B times A. So in this way you get an opposite algebra. And so this gives you S op opposite Severi-Brauer surface. And S op is not isomorphic to S. This is like the classical theory of central simple algebras. Okay, but now with these facts, we can now find all the circuits of links that start from a Severi-Brauer surface. So what can we do? Okay, so we have S, a Severi-Brauer surface. And now let's think, what circuits of link can we do? So I said that, so we need to blow up a point. So, okay, maybe I should also say S is a Mori fiber space over a point just. So I will not write this. So we need to blow up a point. Now we cannot blow up a rational point because it doesn't exist. We cannot blow up a point of degree 2 because it doesn't exist. But there exist points of degree 3, so we can blow up a point of degree 3. Now a point of degree 3, I mean, we have 3 points on S, and we do have an isomorphism over the algebraic closure to P2. And on P2, I mean, we know that we have 3 lines through this point, right? And this gives us also something here on S. So what we can do is we can blow up a point of degree 3. We get some variety X. Maybe let me call it Y. And then we can contract the 3 lines. So contract 3 lines. And now, actually what we get is we don't get S, but we get S op in this way. So yeah, that's not too hard to check for points of degree 3. Okay. So this is a this is a Sarkisov link that one can get from that starts from a Severi-Brauer surface. So what else can we do? So we cannot blow up a point of degree 4 because it doesn't exist. We cannot blow up a point of degree 5 because it doesn't exist. But there can be a point of degree 6. So we blow up a point of degree 6. And again, we see from the picture in P2, when we have 6 points, then we can take like the conic that passes through 5 of the 6 points. So conic, and we can contract that. So contract 6 conics through 5 of the points. And actually, here you get again S op. This is now less obvious. Okay, now what else can we do? So we cannot blow up a point of degree 7 because it doesn't exist. We cannot blow up a point of degree 8 because it doesn't exist. And now we cannot blow up a point of degree 9. And the reason is because we have the condition here that minus kx is pi ample. So in this case, just minus kx ample. And like, so, okay, maybe I should have mentioned this. Let me write it here. So if B is a point, this means that X is a Del Pezzo surface. Okay. And when we are in P2, we cannot blow up 9 points and still get a Del Pezzo surface. Okay. So we are done. Okay. With this argument, we have found all the Sarkisov links. So we just have this and this. These are the only Sarkisov links that start at S, but I mean also when you can do the same with S op and you just get the same things, right? So you're done. There is nothing more. Okay. So now we can also ask about what are the relations between these Sarkisov links? Okay. So who can appear in a relation together? So first of all, let's observe that when we take a Sarkisov links with a 6 point, this cannot appear in any relation with any other link. Okay. Because if it would appear in a relation with a point of degree 3 link, then you would blow up 9 points and you don't get a Del Pezzo. Okay. And in the definition of the relations here, I mean, we took rank 3 fibrations, but so we still have this condition of minus kx being pi ample. Okay. So this is why a link of degree 6 does not appear with a link of degree 3 and also not with a link of degree 6. Okay. So because rank R fibration over a point have to be Del Pezzo, links. So let me write it in this way. 6, 6 do not appear in any non-trivial relation. So the only relation that can happen is when we take 2 links of degree 3. And I have a beautiful picture of that. Okay. So now, of course, you don't know what this picture means. Okay, so what do I mean with this picture? So when we take 2 links. Okay, so we take 3, 3 to S up. Okay, and now this thing here corresponds to S. Blow up a point of degree 3. We go to okay, maybe let me write x6 here also. And then we contract a point of degree 3 and we go to S up. So this is like the information encoded here. And now we take a second link. To some x6 prime. So, and now this link is encoded, let's say in this way here. We blow up a point of degree 3, we get x6 prime, we contract, and we go to S up. Okay. And okay, I will not say more how you get this, but let me now give you the statement of our construction, so the construction of our group homomorphism. So we prove the following theorem. So let S a non-trivial Severi-Brauer surface over a perfect field. Okay, so now I say that I don't know what this letter is called, let's say ED, to be the set of equivalence classes of Sarkis of links. So going from S to S up, where we blow up a point of degree D, contract something of degree D, Sarkis of link. And we mod out by an equivalence relation, which is given by, so chi is equivalent to chi prime. If there exists alpha beta isomorphism such that, so we go, so let's say chi, we have it here, and then here we have chi prime here, and we want that we have alpha and beta in this way. Okay, so this is our equivalence relation. And now there exists a groupoid homomorphism from our groupoid Mori of S to direct sum of set mod 3 free product of set. Here we have E3 and here we have E6. Okay. And the construction is as follows. I send a okay, so chi a Sarkisov link. I send it either onto a 1 indexed by the equivalence class of chi, when chi goes from S to S op, or I send it onto -1 of chi inverse when chi goes from S op to S. Okay, so I mean each element, so each index set has a 1 somewhere, right? And then I send it onto the one given by either his class or by the class of its inverse. Okay, so the classes, they always go from S to S up. They never go into the other direction. Okay. So, and here with this construction, it is important to have S and S up, that they are not isomorphic, but just birational to each other. And actually, the way to prove this theorem, the important thing is just to remark that actually, so in our diagram here with this relation, so let's say we have here, this is chi1, chi2, chi3, chi4, chi5, and we have chi6. And the important thing to remark is that chi1, chi3, and chi5 are equivalent, and chi2, chi4, chi6 are equivalent. Okay, so this is the same as to say that so the yellow ones are equivalent and the green ones are all equivalent. Yeah, and so this is also why we need to get the Z mod 3 here, right? Because we have this relation here. And for the Sarkisov links with points of degree, whoa, what's that? Sorry. Sarkisov links with points of degree 6. We do not have any relation, so this is why we can't go to Z. Okay, so I'm not sure it was very clear, but yeah, I will stop here. Thank you.